I'm very happy to welcome Yusu Wang to CCCG 2020 to give the Godfrey Toussaint Memorial Lecture. Yusu received her PhD degree from Duke University in 2004 under the supervision of Pankaj Agarwal and Herbert Edelsbrunner. After a postdoc at Stanford, she joined Ohio State University in 2005, where she has been until this month. She is now moving to the University of California, San Diego as a professor. Yusu is well known for her work in computational geometry and computational topology. A recent theme of her work is the integration of topological or geometric ideas with machine learning frameworks to develop new data analysis methods. She then applies these methods in domains like computational biology, geometric modeling, computer graphics, and visualization. Yusu is on the editorial boards of Siam Journal of Computing, Computational Geometry, Theory and Applications, and the Journal of Computational Geometry. Welcome, Yusu. We're looking forward to hear about hidden geometric graphs. You can take it away.
All right, so thank you for the introduction and thanks for inviting me. It's really great to be here. Let me start by saying that it's a great honor for me to give this Godfrey Toussaint Memorial Lecture. On Wednesday, Eric already gave a wonderful tribute to Godfrey and mentioned several of his important contributions to the field of computational geometry as an earlier pioneer of the field. I just want to repeat that Godfrey is an amazing person, warm, very funny, full of life, passionate about research and many things beyond. So when I was a PhD student, I was very fortunate that Godfrey invited me to one of his famous workshops on computational geometry in Bellairs Research Institute of McGill University in Barbados. Okay, like Eric mentioned on Wednesday, so this is a week-long workshop where researchers, senior ones, junior ones, come together, live together, working on open problems. And it was an amazing experience, especially for junior people. Godfrey and other participants, they're very dynamic, full of energy, and I never knew that the research could be of so much fun. So I'm very grateful to Godfrey to give me this opportunity and also open new doors to research for me. What I'm going to talk about today is also a tribute to Godfrey. I'm going to talk about the graphs, which is an object well studied in our in the computational geometry field. But what I'm going to focus on today is that using some of our recent explorations as examples to show how geometric and in particular topological ideas can be used to help us to analyze different aspects of graphs for modern data science. All right, so first a few words about the key objects here. Well, geometry for this audience we're all very familiar with. They help us to give us precise ways to describe an object and shape. Okay, topology is probably more alien to some of you here. Nevertheless, you may have heard the saying that topologists are those who cannot distinguish between a coffee mug and a donut, because even though the two do not look the same, don't have the same geometry, they have something common, something essential in common, which is characterized by connectivity. So one can continuously deform to the other without ever breaking and stitching, and vice versa. Okay. All right, so this thing clearly is not true. Nevertheless, it does emphasize the important ability of topology and the topological language in helping us not only to characterize and describe essential features of just the shape itself, but also for functions and maps defined on the shapes and spaces. Okay, so this makes topological methods very powerful and general. By choosing the functions that you are going to inspect carefully, you can even encode the geometric information about the shape as well. All right, so why is this relevant? Well, in the modern data era, we come across diverse, complex data routinely. But this data, they are not arbitrary. Okay, so data has both data themselves and the space where data is sampled from, they have structure and shape behind them. So to this end, geometric and topological methods form a very natural platform for both to help us to describe and characterize the data and shapes themselves, but also to help us to design new algorithms to manipulate and process data. Okay. Indeed, in the past 2 decades or so, the field topological geometric data analysis, TGDA, has attracted a lot of momentum from researchers from computer science, from applied mathematics, and from statistics as well. Okay. So from my point of view, an important component of TGDA is basically combine those mathematical objects and insights together with algorithms to help develop new methodologies for data analysis through the topological geometric lens. So what I want to do today is to using analyzing graph data in this example to show how this geometric and topological ideas can be used. Okay. Well, I assume that I don't have to motivate the study of graphs and the networks, which is by far one of the most common type of data that we encounter. Okay. But the graphs, they come in, they present themselves in different forms. It can be a geometric graph embedded in the Euclidean space, or it can be just a combinatorial graph, weighted or unweighted. Okay. So in the most part of the talk, I'm going to focus on the first topic, where we aim to reconstruct a hidden geometric graph from noisy data, okay, using topological ideas. Okay, and later I would also mention using topological ideas to help to do graph comparison and classification, and I'll briefly mention how to. The last topic is more geometric. I'll briefly mention how to recover the shortest path metric from a randomly perturbed graph. All right, so let's look at the geometric graph reconstruction problem. Well, roughly speaking, we're given some input, say a bunch of points sampled from a hidden geometric graph. Like in this case, say the graph of interest is this red tree-like shape, and the goal is to and the input at this point sample. The goal is to reconstruct a graph G hat, which hopefully approximates the hidden graph G with some guarantee, theoretical guarantee. Okay. All right. So actually, let me give you a more concrete, motivating application. Let's say that we have a collection of GPS trajectories collected by your cell phone, by taxi drivers, and so on. Okay. So you can think of this GPS trajectories as a sample of the hidden road network that we don't see, and the goal is to reconstruct the hidden road network automatically from this trajectory data. Okay, so here, these are the trajectory sampled from downtown Berlin. All right, so this problem is very important, and there has been a line of work on this topic. And some of the challenges include that the GPS trajectory, even with some better technology today, still they can be noisy, especially when you are in the downtown area. A bigger issue is that this trajectory, the sampling, they're highly non-homogeneous. So in downtown area, the sampling is usually much higher. You have many more trajectories compared to when you're in the residential area. Okay? Or even when you are geometrically close locations, you could have a major road, okay, with a lot of cars traversing, intersecting a small road. And then the major road would receive many more samples than the small road, even though they're geometrically close. Okay. Many of the previous methods are very often, they make a decision to decide whether a point is on the road or it's at a junction or not based on local information. This makes it very sensitive to noise, and also some sort of thresholding often involved to remove the noise. Okay, so in general, such local information makes the identification of the graph connectivity in junction nodes very challenging. So we are going to use what I call a persistent guided discrete Morse-based reconstruction framework for this purpose. Okay. As you will see later, here we use the global topological structure behind the data to help us to model and to recover the graph. And using this global structure help us to make the method more robust against noise, small gaps, and more importantly, the non-uniformity in the input data. Okay. And you also see later the algorithm is conceptually very clean, very easy to implement. The code is publicly available on GitHub. I should mention that using discrete Morse theory combined with persistence to recover structures, this is not new. There's been a line of work using this kind of approach to recover sheet-like structure, voids, and so on. Okay, in our approach, we'll see later that by understanding this method better, especially for the specific case of recovering graph case, we significantly simplify the algorithm, also provide theoretical guarantees. Okay, so now instead of thinking for the specific application, instead of thinking that I will input a trajectory, let me first convert that into a density field. Okay, so in the case of GPS traces, just imagine that I sample many points on each trajectory, and I do a kernel density estimation to get a density field defined on R2. So the approach works for high-dimensional data as well, but in this talk, I mostly focus on two-dimensional, three-dimensional data, and illustration is all two-dimensional. Okay. So now we have this density field indicating where the signal is strong or weaker. And if you look at the graph of this density function, treat that as a mountain range, a terrain, okay? Then intuitively, okay, the roads are those places where locally, when we go off the road, the density will trail off, will go down, will become lower. Okay, so intuitively, we can capture the hidden roads using the mountain ridges of this terrain. Okay, so that's the idea. Okay, and in particular, these mountain ridges can be described using a topological object called the one unstable manifold of this function. So in particular, what is this one unstable manifold? So here's a very brief introduction of the, not a full blown up of Morse theory. So let's say we have a nice function called a Morse function. Okay, so defined on RD. In the picture, it's defined on R2, and what you see here is a graph of this function. Okay, now at any given point X, the gradient is here. It basically indicates the steepest descending direction of this function. Okay, so if you put a drop of water on the surface of this graph of this terrain, this is the direction where the water would flow. Okay, if the water continues to flow till it reaches a point where the gradient vanishes. Okay, and those points are the so-called critical points of this function. That's where the gradients become zero vector. So in the two-dimensional function, we have the maximum, this red point, minimum, the blue points, and the saddle points, the green ones. Okay, and the trajectory that this water would flow on the surface of this terrain, the maximum such trajectory is called a flow line, an integral line. Okay, so intuitively, if you think about it, this flow line should start and end at critical points because those are the places where gradients vanishes. Okay, so you can think of the flow line originates and terminates at critical points. Okay, and in general, if I put a drop of water on the surface of this terrain, then it will flow into this minimum, this basin. Okay, however, sometimes you have this flow line actually flow to saddle points. Okay, like this one going from starting from this maximum M2 to the saddle S, and same here. Okay. And this is actually necessary because intuitively, if you are on this side of the mountain, the water would flow to this minimum V1. And if I go to the other side of the mountain, it would flow to this other basin, neighboring basin V2. And somewhere in between, you have to have the transition. The water flow would go to the saddle points, separating the two. Okay. And because of this kind of intuitive to use, so such integral lines that ends at the saddle points for this two-dimensional function or for high-dimensional function ends at the so-called index d-1 saddle points. Okay, so they come from max and end at the saddle point of index d-1. So the union of such integral lines is called one unstable manifold of this function. Okay, as we see here intuitively, this one unstable manifold going from max to saddle, from mountain peak to saddle, from mountain peak to saddle, and they basically circle separating different basins. So intuitively, that gives us the mountain ridges. Okay, so the first idea essentially is to use the one unstable manifold of the density function to describe the mountain ridge and which further to capture the hidden road network. Okay, the hidden graph structure. All right, so this is just an example on the real data from the trajectory data. Okay, now I introduced the idea in the smooth case. Okay, in practice, we're given discrete inputs. So, for example, we could have given a triangulation of the domain, and the function value, the density value, is only available at vertices of this triangulation. So in this case, of course, we can treat the function as a piecewise linear function or other higher order approximation. However, the integral, the gradients, integral line, these are all differential objects. Okay, so using PL approximation makes them numerically not very stable. Okay, later we would also see that the simplification of such differential structures in the PL setting is not as easy as well. So instead, we're going to rely on something called a discrete Morse theory, originally introduced by Foreman in the late 90s. Okay. So this discrete Morse theory is not a discretization of Morse theory. Instead, this is actually a combinatorial version of the Morse theory for cell complexes. Okay. So Foreman proved many beautiful results analogous to classical Morse theory for this discrete, for the cell complexes. Okay. Because of the combinatorial nature, okay, numerically this approach is very stable, okay, and another big advantage is that algorithmically this is much easier to handle, especially when we come to simplification of the density field and the output. Okay, so that'll become more clear in a minute. Okay, all right. So so I will not give you a full description of the discrete Morse theory. Instead, let me only focus on part of the object here, which is the discrete version of the gradient vector field, because our final target, this one unstable manifold, is coming from the study of the gradient vector field. Okay, so now our input is a simplicial complex K, so you can think of this just a triangulation, consists of vertices, edges, triangles, tetrahedrons, and their high dimensional versions glued together nicely. Okay, so in this example here, I show a triangulation of the planar domain here. Okay, okay. So what is a discrete gradient vector? It's actually a pair of simplices where one is the face of the other of codimension 1. Okay, in other words, for example, I could have a vertex paired with an edge that is incident on. Okay, so this pair is a discrete gradient vector. Or I could have an edge paired with a triangle that is incident on. So it's an edge triangle pair, vertex edge pair, or triangle tetrahedron pair, and so on. Okay, so it's really a very combinatorial object, a pair of simplices that's incident to each other. Okay. Now, even though that this is just a pair of simplices, still you can think that this pairing gives us this idea of flow. Okay, so for example, I can imagine that, okay, if I'm at this edge, I can follow the pairing to flow into this triangle. Okay, and then from this triangle, I go to one of its other face and edge, and then continue to flow into another triangle, and so on, continue to follow this. So this would give us a flow path using this pairs of simplices. Okay, so we can still think about this flow path, this V path. Now we call this a V path, which is kind of analogous to the gradient flow integral line in the smooth case. Okay, and we say that a collection of such discrete gradient vectors, namely such pairs, is called a discrete gradient vector field if, number one, no simplex should appear in more than one such vector. This is roughly saying that at any moment I should have only one gradient vector. Okay. The second is that if you follow this kind of V path, this flow path, then all the V paths should be not acyclic. Okay, there shouldn't be cycle. This is because that if you follow gradient vector flow path in the gradient vector field, then your function value along should be monotonic. So it should only go down. You can never come back. So there shouldn't be cycle. Okay. And once a collection of such discrete gradient vectors satisfy these two conditions, then we say we have a valid discrete gradient vector field. Okay, and then naturally, what are the critical, a simplex is critical, analogous to the critical point, if it doesn't appear in any discrete gradient vector, namely the gradient vanishes. So it doesn't have any gradient edit containing it. Okay, so in this example, the pink colored simplexes, like this triangle, this vertex, this edge, these are all critical simplexes because they are not paired with anybody. Okay, all right. So this is very high level, but very hand-wavingly, what I just said is that you can think of this discrete gradient vector field, this collection of pairs between simplexes, kind of analogous to the gradient field for the a nice Morse function defined on a continuous domain. Okay. In particular, let's say that our domain, our input now is a triangulation of d-dimensional Euclidean space. Okay. Then you can roughly think, this is not precise, it's not really correct, but you can roughly think that a critical K simplex, okay, corresponding to, in a smooth case, corresponding to a critical point of the index K. So in the two-dimensional case, you will have a triangulation of the planar domain, like this example, okay? Then critical triangles, that's of dimension triangles, the two-dimensional simplex. So critical triangle basically corresponds to maximum, okay, that's index 2 critical points. And the critical edges, which is index 1, corresponds to saddle. And the critical vertices, index 0, corresponds to minimum in the smooth case. Okay, so you can roughly build this connection. And now remember that we were interested in the one unstable manifold, which is basically the flow line going from max to saddle to max to saddle and so on. Okay, so in this discrete case, this is basically the V path, this discrete flow path, going from critical triangles to edges to triangles to edges, and so on. Okay, now, so this is a two-dimensional case. In general, if your dimension of the domain is higher, then this one unstable manifold corresponds to the V path between d-dimensional simplex to d-1 simplex and alternating. Okay, so this makes it a bit hard to compute and maintain in practice. Okay, so here in later to algorithmically more easily to handle this, we're going to invert our density function. So the maximum becomes minimum now. And instead of to look for this mountain ridges going from max to saddles, now we look for valley ridges going between minima to saddles and so on. Okay. The advantage is that in the discrete setting, okay, such one stable manifold corresponds to the V path between vertex edge. Okay. So this also implies that no matter what the dimension of your domain is, okay, to compute and maintain this one stable manifold, now the value ridges between minima and the saddle, I only need up to the two skeletons of the domain. Namely, I only need the vertices, edges, and the triangles. Okay, so the high dimensional simplexes are not necessary now. Okay, so this this makes the algorithmically computation much easier. All right, so an important operation that's an important advantage of using this discrete Morse theory is the so-called Morse cancellation operation, which can help us to simplify the vector field. What you might simplify, basically reduce the number of critical simplexes. So just like in the smooth case, you try to smooth out the critical points. Okay, so in particular, in the discrete case, a pair of critical simplexes, say the V2 and the E2 pair. Okay, so both of this red right now, they are critical. Okay, so a pair of critical simplexes can be cancelled if there is a unique flow path, V path between them. In this case, it's this black path. Okay, and the cancellation operation is very simple. It's also combinatorial. Namely, you just simply locally invert the orientation, kind of modify the pairing locally, and afterwards both V2 and the E2 become not critical anymore. They are involved in the pairing. Okay, and so so the point that we do need a condition that there's a unique path between these two critical simplices, because this is just analogous to the smooth case, removing a pair of critical points. So we do need this condition of a unique path between two critical simplices, because if there are more than one, like in this case, there are two, this way and this way, and after you cancel it and inverting the direction orientation of one of them, then you form a loop, which means that the resulting vector field is not a valid gradient vector field anymore. Okay, so that's why you have to have this condition. Okay. All right, so that's kind of all the key concepts that I need for the discrete Morse theory. But, okay, to summarize, I mean, what we said is that this discrete setting, the gradient vector are just the pairs of simplices, okay? And we also have this Morse cancellation operation to help us to remove critical points, critical simplices, which would further also simplify the resulting one stable and unstable manifold structure, okay? But the question is that which pairs of critical simplices should we simplify, okay? Any pair can be simplified as long as there's only a unique V path between them. As long as this condition is satisfied, you can cancel this pair of critical simplices. Okay, so how do we decide which pair to simplify? In fact, if you think about it, so far in this discrete Morse setting, I haven't even mentioned the function itself. Okay, so how are we going to leverage our input density function? Okay, so the way we're going to use this is that we're going to use the input density function to tell us, to guide us, which pairs of critical simplices we are going to cancel out to simplify. Okay, and in particular, this is achieved through yet another topological object called persistent homology. Okay, so now this is the last concept I'm going to introduce. So the persistent homology is one of the most important developments in computational topology in the past 2 decades. So here I'm only going to give a very narrow and very simplified view for the so-called persistence induced by the sublevel set filtration of a one-dimensional function. Okay, so it cannot go any simpler than that. Okay, so in this example, let's say that I have this function defined on R, okay, a real valued function defined on R, and this is the graph of the function. Now imagine that I'm going to sweep the domain in increasing function value, okay? And at any moment, say function value A, I keep track of what is the topology of the portion below me. That's the so-called sublevel set of this function at value A, okay? Now, since my input is so simple, it's just R, so the portion below me, I'm going to look at the topology of the portion below me, in particular, the homology group information, okay? Because now we only have one-dimensional case below me. I only need to talk about the zeroth homology information, which essentially just the connected components information, okay? So for example, at this value, I have 2 connected components. And when I move to X1, after I pass X1, what happens is that a new connected component got created, okay? So in the portion I swept through. So we say that X1 creates a topological feature, in this case, a component, okay? And as we continue the same, X2 creates another feature, X3 creates another feature, and at X4, when we pass through this, what happens is that the components created at X3, this little orange colored one, and the one created at X2, they get merged. So I killed the connect component. So I killed the topological feature, okay? And it turned out that there's ways that from the algebraic topology interpretation behind this, you'll see that you can think of that the feature created at X3, really the components of X3 plus X2 got killed, become trivial at the point when I pass X4. So we're going to pair X3 up with X4 intuitively. That means that something created at X3 got killed at X4, okay? And the importance of this persistent pairing is called the persistence of this is simply the function value difference between them. So this is a small low persistent one, okay? And we continue, and at X5, we kill the feature created at X2, get another pairing with a bigger persistence now, and so on. Okay, so in the end, you get a whole bunch of this persistent pairings. Okay, each pair indicates the creation and the death of some topological feature. In this case, it's only zero-dimensional, but in general, you have high-dimensional topological feature as well. Okay, and I can plot the function value of this first and the death of topological features into this first death plane. Okay, so for example, x3, x4, x2, x5 give me the birth of this pairing is the function value at x2, and the death is at x5. I killed it, so this is the first time and the death time. Okay, so this first death plane representation of this persistent features is a so-called persistent diagram. Okay, which every point inside indicates the birth time and death time of some topological features created and killed through this sweeping process. Okay, all right. So now if our input is actually a piecewise linear function defined on a simplicial complex, okay, then we can basically simulate what I just said using the so-called lower star filtration, simulate the sweeping process. And using the standard algorithm, the first persistent algorithm actually proposed by Brunner and et al. So the output of this persistent algorithm will give us a collection now, pairings between simplices now, because our input now are simplicial complex. Okay, but the meaning remains the same. Each pair of such simplices output in the persistent diagram would create correspond to the creator and destroyer of some homological feature. Okay, and its importance is a function value of this function value difference between this pair of simplices. Okay, all right. So with all of this, we now have all the pieces. Okay, so here's the graph reconstruction algorithm. Conceptually, it's just 3 simple steps. So the input is a triangulation K of a d-dimensional domain I, and with a function f defined at vertices of the triangulation. Okay, and let's also given the threshold delta for later simplification. Okay, so what we're going to do is that we're going to start with a trivial discrete gradient vector field where there's no gradient vector at all. Everyone is critical at the beginning. Okay, so that's how we start with this trivial gradient vector field. And then in the first step, I'm going to compute the persistent pairing using the persistent algorithm for the function minus f. The only reason, remember, that we, instead of looking at the density f, we look at the minus f so that I can convert the mountain ridge to the valley ridge. Okay, so the output of step 1 will give us a whole bunch of pairs between simplices, and each pair would have a persistence value associated to them. Okay, then in the second step, we basically go through all these persistent pairs, which are pairs of simplices, whose persistence is low, smaller than our threshold. And then we attempt to perform the Morse cancellation for them. So basically, the idea is that for all those critical simplices whose importance, whose persistence is low, I try to cancel them out. Okay, remember, in a prior, I don't know whether I can do that or not. I have to check whether it's only a unique gradient path between V path between them. Okay, but if I can, I cancel it out. Okay, so then at the end of it, we will simplify all the low persistent critical simplices. Then in the last step, we simply take the remaining critical edges. Remember, this corresponds to the saddles in the smooth case. So we basically take all the remaining saddles whose persistence is larger than my threshold delta, and then collect their one stable manifold. The union of them is my output. That's the algorithm. Okay. So as I mentioned earlier, this algorithm works for any d-dimensional domain. It doesn't have to be a triangulation of RD. Actually, it can be any d-simplex, simplicial complex. But we only need the 2 skeletons of it to carry out the algorithm. Okay, we only need the vertices, edges, and the triangles. Okay. So before I say more about this, just some examples to show the performance here. So this is the reconstruction from the trajectories in Athens, Beijing, and Berlin. So the dark colored graph is our reconstruction, and the light colored background, this light gray colored map is the true map. We don't recover everything because we don't have trajectories over all the roads. Okay. So the Beijing one This is from the taxi driver's trajectory. So this is just to show the simplification of the persistence. When you have a low threshold, you reconstruct many more, and as you increase the persistence threshold, only the kind of the major roads are maintained. Okay. Now this is different from the thresholding wouldn't work in this case, because if you use a low threshold, then in the downtown area, which is here, okay, all the points got maintained, so you cannot see any structures over there. Okay. While if you want to recover the structure here, use a high threshold, then you miss many other low, less sampled regions, the roads from those regions. Okay, and this is just to show that this is previously the state of the art, and this is just to point out that because this discrete Morse-based method using the global topological structure of the sensitive field to recover the roads. So the output tend to be more connected instead of like in the prior work, as the decisions local tend to be more segmented. Okay, so you capture the global structure better here. And you can also use this for map integration and other applications. So this is just a more recent work where we use the combined this reconstruction framework with CNN process the satellite images, train the CNN processing satellite image, and to automatically reconstruct road network from satellite image. And this is a very recent work where we use this to actually we combine this discrete Morse graph input together with the standard unit-like architecture, put them together and co-train them to have a segmentation framework which is more sensitive to the structures. So it gives you better connectivity instead of the standard segmentation framework tend to break at the weak signal. Okay, so this is we use this for the processes detection into the neuron images. You can also use this for three-dimensional images. Again, this is for neurons directly. This is a single neuron reconstruction, and this is a more challenging summarization of the neuron bundles from the whole brain images. Okay, all right. So the method is rather simple, and it also works reasonably well in practice. But what can we say about it, and why should it work? Okay, because if you think about it, in fact, a prior, I'm putting two topological objects, the discrete Morse and the persistent together, even though it sounds like there's some intuition behind them, but it's not clear why should the persistent guided pairing should work with this discrete Morse cancellation, why you don't come across some obstacle in the middle. Okay, so to have some theoretical understanding of this, in fact, as we try to understand why it works, it turned out that this also leads to much simpler algorithms for simpler version of this. So it also gives us a way to edit the editing strategy for the graph reconstruction, because now we know what portions could be missed. So we have specific editing strategy based on that. But more interestingly, we can further simplify this algorithm. Now remember that our algorithm has three steps. The first step, persistent computation. This is just that we use this as a black box, because there's so much work has been put into making persistent computation efficient from different type of input. Okay, so that is a black box, step one. So step two, before I had to go through all the low persistent critical simplicities, pairs of critical simplicities, and try to cancel them out, perform the Morse cancellation operation. Okay, and it turned out that actually we don't need to do that. Okay, in fact, even though the idea coming from maintaining this discrete gradient vector field during this Morse cancellation, this simplification, you actually don't have to explicitly do that at all. All you need to do is that you just need to collect a certain edges based on the output of the persistence, based on their persistence, okay? And the certain edges together form a spanning forest, okay? And this essentially are all the so-called negative edges whose persistence at most is delta, okay? And that's enough for us to collect the later one stable manifold in the next step, okay? So the simplified step two now, once the persistence is computed, the step two only takes a linear time. I just have to go through all the edges once, okay? And now the third step is that based on the simplified discrete gradient vector field, we're supposed to take all the critical edges whose persistence is high and then collect their one stable manifold. Okay. Now all we need to do is that we just take all the critical edge whose persistence is bigger than delta, and then take certain tree paths in the spanning forest that are generated in step 2. Okay. So all you need is a tree traversal algorithm. So other than the time to compute the persistence, you only need a linear time for the remainder of the step 2 and 3. So the algorithm is very simple to implement as well, and this holds in any dimension. Okay. All right. Okay. So this is just with the theoretical understanding, we can simplify the algorithm, but what can you guarantee of the output? And here the situation is a bit trickier. To get some theoretical guarantee, we have to assume the input coming from certain noise model, okay? And the current noise model is very strong. I'm not going to get into detail here, but roughly the current noise model is that you basically around the ground truth, there's a neighborhood region, okay, of width at most omega, such that your density field is significantly higher in this neighborhood than out of this neighborhood. Okay, so it's a very strong noise model. You can think of this noise model. Oops, I don't have the picture. You can think of this as basically that you have a tubular noise, where noise only within a tubular neighborhood of the ground truth graph, but then add some a little bit background noise. Okay, so and under this noise model, we can show that indeed the output graph is geometrically close to the ground truth. And also in it's topologically, it's also homotopy equivalent to the ground truth. Now for graphs, that's not super interesting. That just means they have the same number of independent loops. But in 2D, you can say a little bit stronger, which is that the tubular neighborhood of the ground truth actually deformation retracted to your reconstructed output. Okay. All right. Now, I do want to point out that the current noise model is very simple, but even that is not completely trivial to obtain this theoretical guarantee because a priori it's not even clear that this persistent plus Discrete Morse framework should even work for clean data. Okay, even that wasn't clear at the beginning, and it turned out it doesn't exactly work for the clean data either. Okay, in practice, I do want to point out that the algorithm works pretty well on the non-homogeneous data, unlike what the noise model requires. Okay. All right, so this is the first topic, and I spent far too much time on that. So let me now talk a little bit about graph comparison and classification. Okay, so here, so first I want to actually mention what I call a persistent-based framework for comparing, find the feature representation of a complex object and for comparing or classifying them. Okay, so in particular, suppose we are given a collection of input objects. This object doesn't have to be graph, can be graph, like in this case, there's a neuron tree. Okay, can be a collection of images or connection of point facts, time series data, and so on. Okay, so this what we can do is that for each of these objects, say this tree here, okay, I can put some meaningful discrete function on top of that and create a filtration, which would then map this object to a persistent diagram representation of it. Okay. In other words, now this object, doesn't matter how complex it could be, now got mapped to a point in the space of persistent diagram families. Okay. And you do this for all the input objects. Now you have a collection of points in the space of persistent diagrams. Okay. Now, if we put an appropriate metric structure on the space of persistent diagram, then we can carry out further downstream data analysis processes like classification and so on, using this feature representation. Basically, you use persistent diagram, space of persistent diagram is a feature space for input. Okay. Now, what metrics should you put on top of this space of persistent diagram actually is important, and the classical notions for persistent diagram, the so-called bottleneck distance or the Waterston distance, they don't have, the metric structure don't have nice inner product structure, for example. Okay, so in the past few 10 years, I would say, starting from the persistent landscape by Peter Buchanek, there's been a series of work. This is actually not complete. A series of work on trying to map the persistent diagram to yet another feature space which has inner products, either finite dimensional vector space or infinite dimensional vector space, using either explicit construction or using kernel embedding and so on. Okay. So what we actually recently further this direction is that if you have input label data as well, so we actually did a matched learning for persistent diagram, because in the burst depth plane, it's not always clear that which part of the data is more important. So we perform a matched learning for persistent diagram summary in a data-driven manner, and then using the result learned metric learned representation to represent persistent diagram. Okay, so we apply this to graph classification tasks with some benchmark data sets, and we compare with all the state-of-the-art approaches, both kernel-based, graph kernel-based, graph neural network-based, and also some recent persistent plus deep learning-based approaches. Okay, so this magic learning capture the hidden importance better and give us better classification accuracy on them. Okay, so this is just a high on the coarser classification of graph objects. Okay, but what if you want to compare graphs and then return a pseudo metric in a more refined manner? Okay, so here we again going to use a topological idea here. Okay, so first, given an input graph, I'm going to treat the graph as a metric graph. Okay, so your input graph, any graph, combinatorial graph with a positive edge weight can be viewed as a metric graph. Okay, so basically, so you can think of each of the edge as a length segment, and the weight is its length. Okay, and then given 2 points, the distance between them will just be that you find all possible paths connecting them, the one with the shortest path. Okay, so that would be the distance between any 2 points in the underlying space of this graph. Okay, so any positively weighted graph can be treated as a metric graph, and if it's unweighted, then every edge considered to have weight 1. Okay, so I'm going to view graph as metric graph and then try to compare to input metric graphs. Okay, and if we are trying to, since now a graph is treated as a metric object, metric space, then one of the standard ways to compare them is using the so-called Gromov-Hausdorff distance between general metric spaces. Okay, unfortunately, the Gromov-Hausdorff distance, even for it is indeed hard to compute the Gromov-Hausdorff distance, even for trees with unit edge weights. Okay, and it's also hard to approximate within a factor 3 as well. Okay, we did have a fixed parameter tractable algorithm to approximate the Gromov-Hausdorff distance for trees, but in general, how to extend that to graph is not clear. Okay, so this is a hard problem. So instead now, I'm going to use the topological idea again, and propose something called persistent distortion distance. Okay, so the idea is the following. So given this input graph, this boring blue Y shape here, okay, for every point in the graph, say S, okay, I'm going to look at the distance, the shortest geodesic distance function to S as my function. Okay, so given the graph S, I look at consider the function f of S, which is just a distance to the space point S along this graph. Okay, so from now I have a function on it, I can do my persistence and summarize this function to a persistent diagram. Okay, so in other words, given any point S, I consider the distance to the space point S and I take that as the world view according to S. Okay, and I summarize that to a persistent diagram, which is a point in the space of persistent diagram. And I do this for all points in the graph, all the infinite points in the graph. Okay, so this is the image of this graph in the space of persistent diagram. Okay, so why do I do this? Well, This essentially is an embedding of the input graph into the space of persistence diagram, and this embedding is isometry invariant. And the nice thing is that if I have another graph, G2 here, and I do the same, now they're finally coming to the common space. Okay, once in the common space, ambient space, which is the space of persistence diagram, I can now measure the distance between G1 and G2 by simply using the Hausdorff distance between their images in this common ambient space. Okay, so that's what we did. This is called a persistence distortion distance between graphs. Okay, so some nice property of this distance is that number one, this is a continuous distance measure. So if you have this red segment and this red segment with the blue graph, okay, even though they don't have the same number of nodes, but then they're just different discretization of the same metric graph. Okay, so under this metric, they will have distance 0. Okay, and it's also you can show that it's stable with respect to the Gromov-Hausdorff distance metric. Okay, and you can compute in polynomial time, but I didn't even want to show the number here. It's a pretty bad polynomial time algorithm. Okay, all right. Okay, so let me just spend a couple minutes just introduce what is this loss, this shortest path metric recovery problem from randomly perturbed graph. Okay, so the motivation is the following. Very often in practice, we can view a given observed graph as a noisy one skeleton of some hidden domain that we don't see. Okay, and very often our goals are then to infer information about either the true one skeleton of that hidden domain or about the hidden domain itself from this noisy observation. Okay, and here we're going to focus on the specific information, which is the shortest path information of the true hidden one skeleton, the true graph. Okay, and then when you're given the noisy graph, we want to recover that shortest path information from the noisy graph. But of course, I have to define what do I mean by the true graph and what is this noisy perturbation. Okay, so for this, we introduce the following model. Okay, so we assume that the true graph is constructed as follows. So the vertices, the vertex set V, okay, are sampled IID from a nice measure defined on a nice geodesic space. Okay, so think of that. Suppose the vertices of the graph is actually coming sampled from a uniform measure defined on a nice Riemann manifold. Okay, so for example, and what is the graph? Well, the graph is simply the proximity graph stand by this vertices. Okay, namely, this is our neighborhood graph. Every 2 nodes within our distance will be connected. So this is a slightly more general version of the random geometric graph. Okay, so this is the true graph, which kind of reflects the structure of this hidden geodesic metric space that we don't see. Okay, and so here is a very boring example. Let's say that the true domain is this circle only, and we sample some the true graph is that the nodes are coming from random sampling from this domain, and then we take our neighborhood graph. Okay, and what is the observed graph? Well, this is what we call a PR perturbation of the true graph. In particular, for every edge in the true graph with probability P, I can remove it. Okay, that's P deletion. Or for any edge not in the true graph, so this kind of shortcut long range edge, with probability Q, I can insert it into our observed graph. Okay, so intuitively, you can think of that this model is basically that our true graph is something like a random geometric graph, but yet on top of that, I add some Erdős-Rényi type of perturbation, both in terms of deletion and insertion. Okay, so this is a final graph given to us. Okay, and our goal is to understand this observed graph and also recover the metric structure behind it. Okay, so I will not get into technical detail here. I just want to say that if you assume that this hidden domain has certain nice geometric property, in particular, if the measure that we'll sample the nodes from is so-called LW measure, okay, then we can recover this true shortest path metric of this hidden graph within a factor of 2 by using a simple filtering structure, filtering strategy based on the so-called Jacob index of each edge. Okay, so this two-approximation approach unfortunately cannot handle very large insertion probability Q. Okay, and it turned out that if you use a stronger filtering process based on the so-called edge click number, then you can almost recover the shortest path metric up to a constant factor for almost a constant insertion probability. Of course, the downside of the second result using the edge click number is that it's very hard to compute. Okay, nevertheless, it is to get to that, we actually have to perform analysis of the behavior of edge click number in this kind of overlay of a random geometric graph and a random ER graph, which itself is interesting. Okay. All right, so that's all I want to tell you. I hope that through these examples, I give you some taste of how actually topological geometric idea you're all very familiar with, but also how topological ideas can help you combine with modern data science for data analysis. Okay, so I want to emphasize that a lot of the work, even though that here we are aiming at applied questions in data science, but a lot of the work rooted deeply in our field, in algorithms, in computational geometry. Okay, so there's a close interaction with the algorithm theory. For example, you can summarize all these objects using a topological object. One of them is the so-called contour tree or merge tree. But then how do you compare them? How can you have efficient algorithms to compare them? Then that comes back to the standard question of the tree comparison problem in our field. Okay, but at the same time, we also sometimes have to think how these ideas can be used with modern machine learning pipelines. Okay, this sometimes require us to change the way we think about the objects, some issues which we may never have paid attention before. For example, if you want to combine topological objects into a learning framework, into a loss function, then you have to somehow be able to differentiate that in order to do the gradient descent or not descent. Okay, so that's all the new challenges that comes in. Okay, so last thing I want to mention is that even though it's not touched upon in this talk, but a lot of once we look at the questions in data science, very often that we have to incorporate with more statistical analysis, like statistical convergency or stability, and so on, or how to handle stochastic data. Okay. All right, so with that, I thank you for your attention, and thanks again for inviting me to give me this opportunity to talk to you.
So I see a raised hand from Anna.
Yeah, hello, Yusu. It's Anna here. I had one question about the metric graphs. So your method embeds both graphs in the same space, and then you were using the Hausdorff distance between them?
Right.
Yeah. From the picture, it looked like maybe a Frechet distance would be interesting. Is there a reason why you did not use a Frechet distance instead of Hausdorff distance?
You're definitely right. The Frechet distance would be interesting. It's just that the Frechet distance for graphs is also hard. So if it's just a curve, then yeah. So that's why we went to a Hausdorff distance. But you're completely right that that's why I'm saying that this has a lot of connection to our field, right? Because now we kind of converted this mapping to arbitrary graphs, which in general, one question is that they're not in the common space. So now we can map them into the same common space, but then still we need a good way to compare them. And we can have a good Frechet. I think Frechet for Frechet distance for trees embedded in at least in the plane, I think that's polynomial time solvable. But in general, for graphs, this is hard.
Okay, thank you very much.
Yeah.
Okay, so I see Don and Ovidio here, and we also have a chat question. So let's start with Don then.
Okay, hi, Yusu. I was just curious. So you met in the graph reconstruction stuff. You say that it works in any dimension. Does this kind of reduction to just looking at spanning forests also hold, or was that a planar thing?
Yes, so it holds in any dimension, and that's right. So that's why if we try to extend this algorithm to recover structure beyond one-dimensional, one-dimensional graph. If you want to say you also want to recover sheets, that unfortunately become much harder. But the spanning forest view holds for any simplicial complex.
Okay, so then I have a follow-up then, because I was curious then, how much of that depends on the topology of RD? Like, can you reconstruct, say, curves on a torus?
So there are two issues. One is the theoretical guarantee. One is that whether the algorithm works or not. Okay. So the algorithm actually works for any abstract simplicial complex. So for example, if you give me a bunch of points in high dimension, I can use the Rips complex and so on. Okay. I can in fact also use the measure-based, the weighted Rips complex like you proposed. But from the theoretical guarantee point of view, right now we require that it's coming from a triangulation of the D-dimensional domain.
Okay, thanks.
Okay, maybe next video.
Well, I just wanted to say great talk. It's actually a bit outside my expertise area. One question that I might not have picked it up is you have implemented this algorithm, right?
Right. So it's available on the GitHub. So
excellent. So to what extent have you tested it to see performance?
Right. So we actually used it quite a bit. I showed some examples. So originally coming from the road network reconstruction, but we used quite a lot in the neuron reconstruction. In fact, we have two submissions for 2D and 3D neuron images where basically, in other words, it's run on 2D or 3-dimensional tubes. Okay. So those codes are very robust and they perform quite well. Now, for high-dimensional data, we have tried RNA-seq data. Okay, so this is treated as high-dimensional point clouds.
I see. That's great. I personally highly appreciate this type of results that you can actually apply in practice, test, and they are working well. So many times we get nice theoretical results, but never implemented and never tried in practice. So we all claim applications, right? And yours seems to actually work well in practice. So that's great.
Yeah, thank you. Actually, here we were hoping that we can get stronger theoretical results. Actually, I really hope that people from our field we can, first to see how to get stronger theoretical results, because here the issue is the opposite. Clearly, it works pretty well in practice, but how can we theoretically prove that it works better in many practical situations when the sampling is non-uniform, for example? Yeah.
Okay, so we have a question on the chat, and maybe we can take this question and then move to the next open problem. So the question is, what if the density function is not Morse? Does this happen in practice, and is it difficult to overcome?
Right. So I started with the smooth Morse theory to provide the intuition that we want to use this topological one unstable manifold structure to describe the mountain ridge. Okay. But then in the algorithm, we go to the discrete Morse theory. Okay. And discrete Morse theory actually works for any cell complex. That's number one. Okay. Number two, the way that our algorithm works. Okay. It doesn't have any conditions on the input functions defined as vertices, because as you see, we start with a trivial discrete gradient vector field where everybody is critical. Okay. So it's a valid gradient vector field. And in the middle, we just use the persistent pairing to help us to simplify it. Okay. So the whole process, there's no numerical issues there. So it works for any input F for this discrete setting. The theoretical guarantee works for the triangulation. The input simplicial complex has to be a triangulation of a d-dimensional tube, and the function at vertices, it can be degenerate and so on. However, it has to satisfy this noise model, namely within a neighborhood of the true graph, a tubular neighborhood, it has to be higher than outside of the significant limit. Yeah.
Thanks, Yusu, for being with us today. And why not we just unmute ourselves and clap for Yusu?
Thank you.